welcome to lecture 9 of module 3 of the course called Game Theory and Economics. So far what we have been doing is that we have been taking up several applications of the idea of Nash equilibrium, and what we have done so far are the cases of Cournot equilibrium, Bartrand equilibrium and electoral competition. Today we shall look into another separate field of application of Nash equilibrium, which is known as war of attrition. So, war of attrition is basically trying to model situations where there are two parties who are fighting with each other over some common prey. For example, maybe these two parties are two hunters, or it can be a more general case of two people fighting over any common resource. While fighting, they are inflicting damages to each other. So, fighting is costly to both, and as soon as I give up fighting, that is I concede, then the other party gets that object for which I have been fighting, and the problem is that right at the time when I give up, all throughout this all this time I have been fighting, so that has been costly, and at that point when I give up, I lose the object and there is this cost of fighting also. So, I get a minus payoff in that case, and when the object goes to my rival, there is some valuation that he derives from that object, but he has been fighting also with me. So, that cost of fighting has to be deducted from his valuation to find out what is his final payoff from that from this entire exercise. So, this is more or less the setting. So, this model in a sense it tries to generalize the case of what we have seen before. It was the hog dove game. So, in hog dove game there were two parties who are fighting over some object, and each party can take two sorts of action. It can be aggressive or it can be passive, and depending on the aggression and passivity their payoffs are determined. Here also we are trying to look at similar situation where this idea of giving up could be thought of as the action of being passive, whereas if you are continue to fight, you are being aggressive. So, this is the case then. So, there are two hunters, let us say. So, these are the players. Actions, what are they choosing here? They are choosing at what point of time they are going to concede. So, t, it can vary from 0 to infinity, is the concession time which a player chooses. And thirdly, preferences. This is given by the following payoff function. Suppose I am talking about the payoff of player I, then payoff of player I depends on the concession time it has chosen, which is T I, and it also depends on the time that its rival has chosen, which is T j. So, this is given by minus T I if T I is less than T j, which means if I is the player which gives up first, which concedes first, then whatever time it has chosen to fight, which is T I, is just the total loss. This T I is the total loss that it is accruing, and that is why minus T I is the payoff that it is getting. By the way, in this model we are going to represent this time in the same unit as the valuation of the object. So, one can think that that 1 minute that I keep on fighting with my rival is worth 1 rupee, and rupee is the unit with which I try to denote the value of that object also. What happens if the time that I am devoting to fight is same as the time that he is, my rival, is devoting to fight? So, if T I is equal to T j, then what happens? At that time, in that case, there is a possibility of half that I will get the object. It is not sure that I will get the object, because he has also given the same amount of time in fighting with me. So, in that case I get half of V I. V I is how I value the object. So, V I, this index of I is coming because the valuation of the object can vary from person to person. How I value the object might be different from how my rival values the object. So, V I is different from V j in general. So, half the probability that I will get the object, half multiplied by V I is the expected value of the object to me. From that I subtract the time I spent in fighting, that is T I, and I get the payoff. If my rival concedes first, concedes earlier than me, then I get the object. So, I get V I minus the time that he has spent in fighting with me, because right at the time when he is giving up, I am getting the object. So, when he is giving up, he has fought for T j units of time, and that is the amount of time I also devoted in fighting with him. So, that is the time, that is the time, that value of which I have to deduct from the valuation of the object. So, that is what I am doing here, V I minus T j, if T I is greater than T j. So, this is how the payoff functions of both the players look like. If I is equal to 1, j is equal to 2, if I is equal to 2, j is equal to 1. Now, before we try to find out what is the Nash equilibrium, here the policy that we are going to take to find the Nash equilibrium is the same strategy that we have been following so far. We are going to construct the best response functions and try to see at what points or point they intersect with each other. Those points will be the Nash equilibrium. Now, before we try to find out what are the best response functions of these two players, let us try to figure out what is going on here. Now, obviously, my payoff from fighting, from this war, is dependent on the time that he, that is my rival, is spending in fighting with me. Now, if I know that my rival is going to spend not a long time, very short period of time to fight with me, in that case it is worthwhile for me to see him off, to fight with him, because I know that he is going to give up after a brief period of time. So, if I devote that time in fighting with him, I will get the object, and if the valuation of the object is quite a bit, then I am getting some positive payoff out of this fighting. So, what becomes important is how T2 is, if I am the player 1, how T2 is compared to my valuation, that is V1. So, that is becoming crucial. Is T2 greater than V1 or is T2 less than V1? If T2 is less than V1, then it is worthwhile for me to fight. On the other hand, if T2 is very high, suppose, in that case it might be greater than V1 also. If it is greater than V1, then it is no way worthwhile for me to fight with him, because longer I fight, the more costly it is for me. And so, in that case I should give up immediately, I should not fight. So, these are the basic ideas which will influence the result of this model. Let us try to look at it in a more systematic way. I can draw the following diagrams. Suppose in this diagram, along the horizontal axis I am taking Ti, that is the time devoted by player 1, and suppose Vi is here. It is given, it is a parameter. Now, we have just seen that what is important is how the time of the other player, that is Tj, compares to Vi. So, there can be broadly three cases. One is Tj is less than Vi. Suppose Tj is here. Now, depending on different values of Ti, there will be different values for the payoff. If Ti is somewhere in this range, is less than Tj, then I know the payoff is going to be represented by a 45-degree line. This angle is 45 degree, except for the point here. So, this point is not included. If Ti is just equal to Tj, the player gets half of Vi minus Tj. So, half of Vi is somewhere here minus Tj. So, it is negative. This is what the player gets. And if Ti is greater than Tj, then player 2 is conceding first, player J is conceding first, then player I is getting the object, and what it is getting is Vi minus Tj, and Vi minus Tj remains as it is as Ti goes on rising. So, this is the line. Now, one thing which should be clear from this is that once my rival is giving up and I am getting the object, it does not matter how much T I had committed in the beginning. So, even if T is very high, it is not affecting my payoff as long as Tj is here in this, which is less than Vi, and as long as my Ti is greater than his Tj. Now, if this is the situation, then what is the optimal time that player I shall devote in fighting this war? So, every player I know is going to maximize the payoff. Here the maximum value of the payoff function is occurring when Ti is strictly greater than Tj. In that case, this is the value of the payoff, which is positive, and this cannot be bettered. So, that is what the best response function of I should look like if Tj is less than Vi then Ti should be strictly greater than Tj. This is what we are going to write down a little bit later. This is the case of Vi equaling Tj. So, like before, we have this 45-degree line, except this point. At this point, he is getting half Vi minus Tj. So, this is the point which is representing his payoff if Ti is equal to Tj, and if Ti is greater than Tj, then his payoff is Vi minus Tj, which is 0. So, it is coinciding with this axis. Here also and this point is not included, this point is not included. Here also the aim of the player I is to maximize the payoff. Now, if he wants to maximize the payoff, the maximum payoff that he can get is 0, otherwise it is negative, and 0 is obtained in two cases. One is that Ti is equal to 0, this point origin, or if Ti is strictly greater than Tj. In that case also he is coinciding, payoff function is coinciding with the horizontal axis and the player is getting 0. Finally, we shall consider the case of Tj greater than Vi. So, here as before, as long as Ti is less than Tj, it is going to be this 45-degree line. At this point, it is going to be half of Vi minus Tj. So, I am getting this point is excluded, and if Ti is greater than Tj, then what the player is getting is Vi minus Tj, which is negative. So, I am getting this line, parallel line to the horizontal axis, and so, in this case the best player I can do is to get 0, and that he gets if Ti is equal to 0. So, putting all this together, suppose I want to write down the best response function of player 1. Ti. Let us see how it will look like. Firstly, if T2 is less than Vi, this case, this is Tj is equal to Vi, this is Tj is greater than Vi. If T2 is less than V1, then I know that player 1 is going to choose T1 strictly greater than T2. Secondly, let us take the second case. If T2 is just equal to V1, this case, the case in between, in that case there are two best response, there are two sets of best responses. One is T1 is equal to 0, or T1 is strictly greater than Tj, T2. So, this is the range that I am talking about, or strictly greater than T2 if T2 is equal to V1. And finally, if T2 is greater than V1, then I know that player 1 will choose only 0. So, T1 is equal to 0 if T2 is greater than V1. So, this is the best response function of player 1. For player 2 it will be similar. Let me just write it down. Okay. So, this is how the best response functions are, and we can now draw the best response functions and find out the intersection points. So, suppose let us suppose without loss of generality that V1 is strictly greater than V2. So, V2 is here, this is the and V1 is here suppose. First let us draw this best response function of player 1 B1 T2. If T2 is less than V1, then T1 is strictly greater than T2. So, this is the point 45° line. I can imagine this is the 45° line. If T2 is less than V1, then T1 should be strictly greater than T2. Now, this point is not included because T1 has to be strictly greater than T2, and if T2 is equal to V1, T1 is either 0 or T1 is strictly greater than T2. So, this point is not included, this point is included. If T2 is greater than V1, T1 is equal to 0. So, I am taking this axis. So, this is how the best response function of player 1 looks like. What about the best response function of player 2? If T1 is less than V2, T1 is less than V2, I am talking about this, then T2 is strictly greater than T1. So, this axis is included, entire axis except the origin, and all these points are included. The points on the 45 degree are not included. If T1 is equal to V2, then either T2 is equal to 0. So, this point, or T2 is strictly greater than T1. So, this line is included. If T1 is greater than V2, then T2 is equal to 0. So, this axis itself. So, this is how it looks like. Now, putting these things, two things together, what we have found is the Nash equilibria or the points where the two base station functions are overlapping with each other are occurring in this part, that is in V2 and greater than V2 if T1 is equal to V2 or greater than V2 and T2 is equal to 0, or in this part, that is T1 is equal to 0, T2 is equal to V1 or greater than V1. So, Nash equilibria T1 is equal to 0, we are talking about this, or T1 is strictly greater than equal to V2, T2 is equal to 0. So, there are two sets of Nash equilibria here. In particular, there are infinite number of Nash equilibria. Now, this is the result, but what does it mean? What is the intuition? The intuition is that let us talk about this first set of equilibria, that is T1 is equal to 0, T2 is greater than equal to V1. Here T2, that is player 2's time, concession time, is either equal to player 1's valuation or greater than player 1's valuation. Now, in this case obviously, if player 1 wants to fight with player 2, either he will get 0, because if T1, if T2 is equal to V1 and T1 is also equal to V1, then in fact player 1 will get negative payoff. So, there is no way he can get a 0 payoff either. If T2 is greater than V1, player 1 can fight with player 2 and can win the object, but its payoff is going to be negative because V1 minus T2 is going to be negative. So, by deviating, by choosing any positive time, player 1 can only be worse off. So, that is why he is sticking to 0. From player 2's point of view also, it is not worthwhile to do something else, because here what is the payoff of player 2? Player 2's payoff is in this Nash equilibrium, it is getting V2 minus Tj, which is T1, which is equal to V2, because T1 is equal to 0. So, player 2 is getting the entire value of the object, he is not losing anything, and so this is the best thing he can do, he cannot deviate and be better off. So, that is why this is a Nash equilibrium from both sides. Say by similar logic, this is also a Nash equilibrium. In the second case, it is player 1 who is getting the object, player 2 is not getting the object. So, that is how it is. Now, some quick observations. First is that in this Nash equilibrium, there is no fight in equilibrium, because you see one of the players is always giving up in the beginning itself, he is not fighting. the other player is announcing some fighting time, but since the other player, the first player is not fighting, which in fact means that in the equilibrium there is no fight. Secondly, who obtains the object which means that in the equilibrium it may very well happen that I value the object less and still I get the object. So, it is not necessary that the player who values the object more, he or she will get the object. In this case, for example, we had assumed that V1 is equal to V2 is greater than V2, that is player 1 values the object more than player 2, but we had this equilibrium. Here player 1 is not getting the object, but player 2 is getting the object. So, it means that even if you value the object less, you might still get the object. And finally, the equilibrium is asymmetric. If one remembers the definition of symmetric game and symmetric equilibrium, if we make this game into a symmetric game by assuming V1 is equal to V2, then the game becomes a symmetric game. Now, in that case, it does not mean that we have a equilibrium which is symmetric, because in the equilibrium the actions of players are different, they are not the same, and that was the property of the symmetric equilibrium. So, that the actions must be the same. So, this game does not have any symmetric equilibrium, even if we make the game symmetric. Now, on this idea of war of attrition, we can look some other aspects of this war of attrition. This is a variation of this original game. Each player attaches no value to the time spent waiting for the other player to concede, but the object in dispute loses value as time passes. Assume that the value of the object to each player I after t units of time is Vi minus t, and the value of a 50% chance of obtaining the object is half of Vi minus t. Specify the strategic game that models this situation, construct the player's best response functions, and find the Nash equilibria of the game. So, here what is important is that I do not attach any value to the time that I am spending in getting the object, but the object itself is depleting. So, more we fight, the more the object depletes. So, suppose what difference does it make to the original model? The difference it makes is that suppose I concede first and he is getting the object. In the original game it was the case that I was getting minus Ti if Ti is less than Tj, and in this case I do not attach any value to this time that I spent. So, in that case when Ti is less than Tj, the payoff of player I will be 0 in this case instead of minus Ti. And second difference that we are seeing here is there is if the two players are conceding at the same point of time, then each is getting half of Vi minus t. So, that is also something different. In the previous case we had half of Vi then minus Ti if Ti and Tj are equal. Okay, so this is an exercise about war of attrition. Let me first write down the exercise, the question of the exercise, and then we shall try to solve it. So, this is the direct argument for Nash equilibrium in war of attrition. So, this is the question. Give a direct argument not using information about the entire best response functions for the set of Nash equilibria of the war of attrition. First, let us remember what was the Nash equilibrium or the set of Nash equilibria in the war of attrition game. Then we shall try to give a direct argument why is it so. So, there are two sets of Nash equilibria. One is this set, T 1 is equal to 0 and the T 2s are all greater than or equal to V 1, and V 1 is, remember, the valuation of player 1 for the object. This is one set of Nash equilibria, and the other set of Nash equilibria is that T 2 is equal to 0, that is player 2 is spending no time, and T 1 is greater than or equal to V 2. V 2 is the valuation of player 2 for the object. Now, how do we prove that this is indeed the Nash equilibria? What we are going to do is that we are going to rule out all other pairs of T 1 and T 2 as candidates for Nash equilibrium. Okay. So, what is the complementary set or what are the other possibilities? Other pairs of T 1, T 2 could be the following cases. Case 1, T 1 is equal to T 2. Remember, in this case, in the Nash equilibrium, since V 1 and V 2 are always greater than 0, it is never the case in Nash equilibrium that T 1 is equal to T 2. So, if we rule out this case T 1 is equal to T 2, that basically gets rid of a lot of possibilities. So, why T 1 is equal to T 2 not a Nash equilibrium candidate? If T 1 is equal to T 2, then each player has a profitable deviation. How do I know that? Because at T 1 is equal to T 2, what is U I? U I is equal to half of V I minus T I, right. This is the payoff function in war of attrition game. So, if player I can be 1 or 2, increases her T I by infinitesimal small amount, then her payoff becomes he gets in this case the complete V I minus T j, which is time spent by j. Now, remember between 1 and 2, between 1 and 2, T I is equal to T j, because the other player's time in case of 1 was equal to T I. Here T I is equal to T j. So, therefore, in 2 I's payoff is greater, thus there is a profitable deviation. So, T 1 is equal to T 2 is not Nash equilibrium. Now, this is case 1. What are the other cases? The other cases are the following. Case 2. Let us suppose T I and T j are not equal, and the T which is less, suppose that is T I, is greater than 0. So, this is one possibility, that T I and T j are not equal, but the lower T is still greater than 0. Remember, this is ruled out in the, this is not the case in Nash equilibrium, because in the Nash equilibrium the lower T is always equal to 0. Now, can this be a Nash equilibrium? This cannot be a Nash equilibrium because here u I is equal to minus T I. If I chooses T I is equal to 0, then her payoff rises to 0. So, 0 less than T I less than T j cannot be a Nash equilibrium. So, this is the second case which is being ruled out. What is the third case that can be there and which has to be ruled out? It is the case that suppose T I is equal to 0, but T j is not greater than V I, T j is less than, strictly less than V I. That again we have to rule out. So, this is case 3. Sorry, this is just equal to T I and this is less than V I. All right. Now, why this is not a Nash equilibrium? This is not a Nash equilibrium because what is player I getting here? U I is equal to 0 because he is spending no time, he is giving up in the very beginning. So, the payoff that he is receiving is also 0, but can he do better off? But he can choose T I strictly greater than T j, where T I is less than V I. Because remember T j is less than V I, so there is a gap between T j and V I. Player I can place his T I in that gap. If he does so, his payoff becomes V I minus T j, and which is greater than 0. Therefore, he has a profitable deviation hence 0 equal to T I strictly less than T j strictly less than V I cannot be a Nash equilibrium, or let us say cannot be Nash equilibria, because here there are many possibilities are there. All right. So, the only possibility we are left with is 0 is equal to T I, right, less than T j, and this T j could be greater than V I. So, let us write it like this. Okay. So, this is the only possibility that we are left with. This is a Nash equilibrium. Why this is a Nash equilibrium? Or let us say this is these are Nash equilibria. Because no player can deviate and be better off. Player J is getting the maximum that he can get. So, there is no possibility of improving his payoff. Player I also cannot deviate and be better off, because the other player's T is greater than his valuation. Before we wrap up this lecture, what we have been doing in this lecture, let me sum it up. We have introduced a new concept, a new application of Nash equilibrium in this lecture, which is called the war of attrition, where the two parties are fighting over some common object. The longer they fight, the worse it is for both of them. And if the players think that by by fighting more, fighting for a longer time, they can get the object. So, that is what they are trying to do. They are going to get, they are trying to get as much payoff from the from this fight as possible. But we have seen that in the Nash equilibrium, what will happen is that only one player will get the object and the other player is not going to fight. So, in the equilibrium there is not going to be any fight. Either player 1 gets the object or the player 2 gets the object. The player who is not getting the object is going to concede immediately, he is not going to fight. And this is a case where the equilibrium is asymmetric, in the sense that the time that players say that they are going to fight for in the equilibrium, they are going to be different. So, that is the conclusion of this model. We have considered one variation of the model, and we have seen that in that variation also the equilibrium is such that only one player is getting the object, and the equilibrium is asymmetric in the sense that the times are different. Thank you. Briefly describe the war of attrition game. So, let us describe the war of attrition game. Two players, actions, so Ti is non-negative number. Each player is choosing a Ti, and this is what is known as a concession time, the time at which you are conceding the game to the others. In effect, the game is a waiting game. Two players are waiting for the other to concede, for the other player to concede. If any player concedes earlier than his rival, then that player loses the object. There is an object thereafter. If I concede before my competitor, the object goes to the other player, and while I was waiting for this object, I was incurring some cost also. So, the preferences can be written by this. So, this is the payoff of player I, given that he has chosen Ti and the other player has chosen Tj. So, if he concedes earlier, but he has already waited for Ti amount of time, and that is costly. So, he loses this amount of time, which is minus Ti. What if they concede at the same time? Then there is a half probability, half chance that each will get the object. So, in this case, if Ti is equal to Tj, with half probability I will get the object, all right, and the valuation of the object to player I is given by Vi. So, half Vi minus Ti, the time that has been spent in waiting, and this is equal to Vi minus Tj if Ti is greater than Tj. So, if I have waited for more for a longer time than my competitor, then I get Vi minus Tj. Tj is the time at which my competitor gives up. What are the Nash equilibria in the war of attrition game? What are its properties? So, Nash equilibrium in war of attrition game is given by the following. There are infinite Nash equilibrium. One set of Nash equilibria is given by this, and the other set is given by this. So, in the first case, player 1 gives up immediately and player 2 gives up after after V1. In the second case, player 2 gives up immediately and player 1 gives up after V2. Properties: there is no fight. Because in each case one player is giving up immediately, nobody is waiting for the other player to concede, yes. Allocation of object is independent of one's valuation. So, it might very well be the case that V1 is greater than V2, but player 2 could get the object. Thirdly, equilibria are asymmetric. Okay, asymmetric equilibria, in the sense, this is not the strict definition of symmetric equilibrium and asymmetric equilibrium. What we mean is that in equilibrium the times are different, and this property of a non-equal time will hold even if we make the game sort of symmetric by assuming V1 is equal to V2. Even if the valuation of the first player is equal to the valuation of the second player, in equilibrium there will be no such outcome where T1 is equal to T2. So, these are the answers to the exercise.